In this video, we will briefly discuss saturated versus unsaturated solutions and how the saturation of a solution can be increased. So we just want to really quickly clean up some terms. If we have an unsaturated solution, that is a solution where the solute is still soluble. And so at this point, we contain less than the amount of solute. We can keep adding more solute in, and it will keep dissolving. On the other hand, a saturated solution has the maximum amount of solute that can dissolve under these conditions. Now, in Chem 151, we talked about soluble versus insoluble. An insoluble compound is something that becomes saturated almost immediately. Right? On the other hand, soluble compounds can still reach a saturation point. There is a point where you can dissolve no more sugar into water. There's a point where you can dissolve no more salt into a solution as well. And so at this point, we reached a dynamic equilibrium between the dissolved particles and the undissolved particles. And so these dissolved particles are kind of floating around in solution, and something happens. Say some of the solvent evaporates, and now there's not enough water molecules to hold that ion in solution anymore, so it crystallizes out. On the other hand, some of those water molecules can redissolve another piece of salt from somewhere else. And so as long as the amount of solvent stays the same, we are going to say that the amount of solute that is recrystallized at the bottom of the flask is also going to stay the same. So that's what we mean by a dynamic equilibrium. Generally, what we see is that salt solubility, and for that matter, sugar solubility, most molecules dissolve more at higher temperature. And the reason why is because these water molecules need to surround the solute in order for it to dissolve. Well, the higher temperature water molecules, the more movement, right? Movement is kinetic energy. Kinetic energy is related to temperature. So as the temperature goes up, these water molecules can move around more. And so that increased movement means it takes fewer molecules to completely surround one of these solutes. And so you can especially see as these ions get bigger, ClO3, K2Cr2O7, potassium chromate, potassium nitrate, right? As these ions get bigger and bigger, we generally see a much larger increase in solubility with temperature, right? That increased movement helps the water molecules surround that ion. And in fact, you can play a little game here. One is to kind of crystallize these compounds. So you heat this compound up and increase the solubility, and then you let it cool down very slowly. And if you keep boiling it at high temperatures, it may start to crystallize a little bit. And once you crystallize it, as you cool it down, right, that thing will crystallize out all the way. It's one way of getting a really clean crystalline sample. It's also how they make rock candy, essentially. Okay, so usually you have some kind of agitation with the rock candy. It's the string, for example, that gets it to start crystallizing. There's another thing you can do here, which is you can create a supersaturated solution where you increase the temperature all the way up and then let it cool with no agitation at all. And even though it's cooling down and the solubility should be going down, as long as the water molecules are still surrounding that ion, it doesn't precipitate. And so you end up with a lot more solute in solution than there should be for that temperature, right? And so this is what we call supersaturated. It's got more ions in solution than it should be to precipitate. So you can actually see if you take this cooled supersaturated solution and you add a single grain of solute, well, the water now tries to dissolve that new solute, but it can't. And so it leaves the solute it's currently dissolving to try and dissolve the new stuff. Well, that new solute then tries to get dissolved by the water molecules next to it. And each time they try to dissolve this new piece of solute, it leaves more solute precipitating behind it that it can't hope to redissolve. And so we go from a single grain of solute to soon the entire solution is covered in salt all the way through. So there's a bunch of videos on YouTube about this. A lot of them are pretty amusing. And I'll see if I can add one in here. It's worth mentioning that the opposite is true with gases. And it really comes down to the same idea. When you have a solid dissolving into liquid, right, the solid doesn't move very much. Solids have a low kinetic energy, but increasing the temperature increases the kinetic energy of the liquid and helps them dissolve. Well, gases have the most kinetic energy. So if you think about this water molecule trying to surround this gas, and as the temperature goes up, that gas molecule wiggles around more and more and more, it eventually is going to bust free from the surface. It's going to be hard for that water to hold on to that gas. And so we see, gas storage goes way, way down at high temperatures. This is why carbonated soft drinks are more bubbly in the refrigerator, because at colder temperature they can hold on to more of that gas. It also happens warm lakes have less O2 than cold lakes. So this can be a real problem with a warming climate. What we can suddenly see is if these lakes start getting too hot, the fish don't have enough oxygen to breathe anymore, and they suddenly die off. It's also a big problem they're worried about with global climate change because these oceans have dissolved billions of tons of CO2. And if we get an ocean temperature that's high enough, the ocean itself is going to start adding CO2 into the atmosphere. And that CO2 would increase the temperature, which would cause more CO2 to leave from the ocean. And it's a feedback loop, and no one knows what happens next if that starts to happen. One other way of increasing gas solubility is by dramatically increasing the pressure. This is known as Henry law. If you have a lot of gas pressure, these gas molecules really push against each other as they bump into each other, and they force that gas into the liquid solution. And that only works as long as the pressure is high. The second that pressure is released, if you open the cap of that soda, all that CO2 starts to push itself out, and since it's not pushing back in, you suddenly end up with a flat CO2-less soda. So this happens all the time. I used to have a roommate. He used to buy these big 2 liters of soda, and he would open it once, and then he would forget about it for 5 days, and then he would come back and be like, oh, this is gross, it's flat. Well, over all that time, the CO2 had been just kind of bleeding out of the soda, even though the cap was closed.